My name's David McCaughey. I recently completed my PhD at the University of Stirling in partnership with Historic Environment Scotland. And today I'm going to talk about just one part of my research, and that focused on the effects of climate change on the weathering of Torridonian sandstone that's incorporated in Clachtol Broch. So heritage scientists realise that with climate change, important heritage sites will be exposed to more extreme climatic conditions, having potentially destructive consequences. Reflected in this, Historic Environment Scotland's 2018 risk assessment on climate change shows how Scotland's climate's changed markedly in the last 60 years or so. So on the figure on the left-hand side, you can see that we're currently experiencing fewer days of frost and snow cover, an increased growing season, rising temperature, increased rainfall, and a rising sea level. Now, all of these factors influence our historic environment and its longevity. Now, alarmingly, in that risk assessment, they found that 89% of the 352 sites that they investigated are at high or very high risk associated with climate change between 2040 and 2069. So my research really began off the back of this risk assessment, and I was tasked with forecasting the effect that climate change could have on sandstone heritage in Scotland. Sandstone being an important building stone from the Neolithic to the present day, but is vulnerable to weathering brought about by climate change. So the overarching question in my PhD was, what impact will climate change have on the weathering of sandstones that are incorporated within built structures? And in order to achieve that, I had to develop an innovative research design that integrates the complex weathering processes with the built environment and climate projection data. Now, other studies in the wider literature tend to focus on sort of pristine sandstone that's been recently quarried. However, I find that loses a crucial relatability to the built environment. So culturally significant stone, likes of the stone that's taken from Clachtol Broch, has a memory effect embedded within it, whereby decades, centuries, or even millennia of above ground exposure leave an observable mark in the stone, which sets it apart from the pristine material. So to gain insight into climate change impacts on heritage sites, you have to use this culturally significant material, because the climate change impacts can then be superimposed upon the past weathering history of the stone. If you use pristine material, it doesn't have that crucial past history of exposure within it. So in an effort to fill that literature gap, I was led to Broch structures, and today I'll focus on my research at Clachtol. The question I get asked quite a lot actually is, why Brochs? And although I am particularly interested in them on a purely non-scientific basis, I just find them to be very interesting structures. They have an undeniable cultural significance, and they are unique to Scotland. But from a scientific perspective, they keep a lot of factors in my research constant. They're dry stone, composed of relatively unprocessed material, and have a unique architecture and a similar exposure history of around 2,000 years. So Clachtol was one of my chosen sites due to its particular cultural significance. Setting within the North West Highlands Geopark, and it's been the subject of extensive archaeological investigation. So there's an abundance of this culturally significant sandstone in the archaeological spoil material that I could access and analyse. And as I mentioned, using this culturally significant sandstone is really beneficial for my research. So sandstone samples were taken from archaeological spoil associated with the Broch, and their weathered stone have been exposed since around the Iron Age. But to serve as a baseline to these samples, I also obtained pristine samples from the background geology. These are geological outcrops close to the Broch itself. Now, I analysed my samples in lots of different techniques, but today I'm focusing on petrographic thin section analysis and scanning electron microscope mapping. And these techniques allow microscopic insight into the sandstone structure, its chemical composition, and weathering features. And what I was really interested in is a sandstone life cycle. So from its geological deposition hundreds of millions of years ago to its removal from the geology and use as a building material, where it's exposed to climatic conditions. And then on to the future, where it's exposed to more extreme climatic conditions in a climate change future. And each of these distinct stages of the life cycle having an observable impact on the stone that I can see through the analytical techniques. Apologies. The first stage of the life cycle is from the geology to the broch. So comparisons are made between the pristine material and the broch material to understand how the sandstone is weathered to date and to try and pick out some of the weaknesses. So Clachdal broch, as I've mentioned, is composed of Torridonian sandstone. It's an alluvial red arkose and is extremely robust. It's a particularly coarse-grained sandstone with a high feldspar content, and the majority of its mineral constituents are derived from the Lewisian gneiss, which it overlays. It's predominantly a grain-supported stone, really tightly packed quartz and feldspar grains, and it's held within an iron oxide cement. However, it does contain several weaknesses. And on the thin section images on the left-hand side of your screen, you can see that it goes from a really coarse-grained material to a fine-grained material punctuated by a distinct clay band. And there's also surface loss at the surface of that sample, where the fine material and the clay material is being lost and exposes this coarse material beneath. And as well, from the thin section image on the right-hand side, you can see that there are micro cracks throughout the sample structure, leaving it exposed to water ingress and freeze thaw. And the slides keep getting muddled up and going in the wrong order here. Okay, sorry about that. So at the University of Stirling, we have a controlled environment facility, or CEF for short, where samples can be placed in a climate chamber and exposed to highly specific temperature, humidity and precipitation fluctuations, which allowed me as a researcher to effectively expose the samples to climate change in a simulated manner and analyse their response. So this was very much informed from Historic Environment Scotland's risk assessment that I mentioned at the very beginning of this talk. And I ran two experiments. So the first one was called a climate changed year, where samples were exposed to temperature, humidity and precipitation parameters that are anticipated in 2055. So the data was obtained from the UKCP 18, which is the most up-to-date climate projection database in the UK. And as I mentioned earlier, as part of my research design, I wanted to have a relatability to real climate data, and that's what these climate projections give me. There are other research projects that utilise these CEF chambers to expose stone to weathering, simulated weathering, but they don't tend to use actual climate projection data. So samples were exposed for 12 weeks, and given the length of my PhD, I was able to simulate that period within 12 weeks, which means each week represented a month of real-time exposure. So if you look at the temperature graph in the top left-hand side, temperature fluctuated between the daily minimum and daily maximum temperature while remaining within the sort of mean temperature. On the graph in the top right, humidity remained constant for each week, and the graph on the bottom is rainfall, which was sprayed on samples for a comparative number of days based on how many days of rain per month. So for example, we'll talk you through January. So the minimum temperature is around 2 degrees, maximum around about 7 degrees. And through the week that represents January, I was able to cycle those temperatures hourly to expose the samples to those range in temperatures. Humidity remained constant for the duration of the week, and just under 40 millimeters of rainfall was sprayed onto the samples on 5 of the 7 days of the week. There's typically about 21 days of rain in January at Clachdal, which is roughly around 5 and 7 days of the week. So that's the climate change chamber, but alongside that there's a control chamber which exposed samples to 2018 conditions in the exact same way, but it's just different numbers, so that the effects of climate change can be disentangled from the effects on the samples that would occur without a significant change in climate between now and 2055. So sample response in this experiment was limited in the Torridonian sandstone, which is testament to its robustness. There's slight evidence of granular losses at the base of each sample, but in the before and after images, if you look along the bottom edge of the sample, and in the thin section image at the bottom left, you can see very slight indications of granular losses. But other than that, the identified weaknesses of clay bands, microcracks, all remained intact. But it's important to put those results in context because at Clactaw with Torridonian sandstone, you are dealing with a very robust sandstone. I also exposed samples from Borwick Broch on Orkney to the exact same treatment, and they elicited a far more destructive response. Image in the top left is before and after the experiment. You can see a failure of a pre-existing microcrack. On the bottom left, you can see formation of salt within the samples, which is linked to an extent with climate change. On the top right-hand side, you can also see these dark nodules within the sandstone, and these are sulfide nodules. So basically, when they react, they contain sulfur, which mixed with water produces a sulfuric acid, which dissolves the stone material around them, and that occurred as a result of the experiment. And we've seen quite aggressive microcracking going on within samples. So that's just to set the responses of the Torridonian sandstone against another sandstone type. Because in a climate change future, it's not enough to say this is how sandstones in general will weather. You actually have to look at different sandstone types because they will all react differently. Leading on from that first experiment, I then set up a second experiment that was a bit lengthier with increased exposure to see if that would elicit a response in the Torridonian sandstone. So again, from the United Kingdom climate projections, I collected data this time of minimum, mean and maximum air temperature, as well as mean relative humidity from 2025 to 2055 to try and bridge the gap between present day and the climate changed year, which was my first experiment. So each day in the CEF corresponded to a season. The experiment ran for 120 days to mimic 30 years of seasonal cycling, and this was to really emphasize the transition between seasons, which is forecast to elicit a response in sandstone types. And crucially, samples used in this experiment were relatable to samples used in experiment 1, so that I could, build up this life cycle of the sandstone. And once again, there was a control experiment run in a separate chamber that ran at 2018 conditions in order for me to tell the difference again of what the impact of climate change actually is. So sample response in this case was more pronounced with increased exposure. You see more prevalent granular loss along the bottom of the samples in the before and after images, and that's also reflected in the petrographic thin section analysis images where arrows point to distinct areas where stone material has been lost. Now over on the right hand side, this is a scanning electron microscope map. So the upper map shows quartz in sort of yellow orangey colour and carbon in the bottom. Now carbon basically represents the space within the sample. So those are areas where granular loss has occurred, giving an indication in a climate change future within Torridonian sandstone, we'll see an increased occurrence of granular losses. Furthermore, as I mentioned, these clay bands as distinct layers of weakness, you can see that's where material loss is occurring as well. These are thin section images. So you can see that the clay layer with lost material, and it as well has impacted the coarse grained material and the fine grained material within the sandstone. On the right hand side is another scan electron microscope map. And this is the sample surface. We started to see vertical microcracking going on in the samples, which isn't something that we had seen in the samples before then. So this leaves the surface of the sample exposed to water ingress and processes such as freeze thaw. So from this evidence, it appears that Torridonian sandstone samples are prone to granular and surface losses, particularly along lateral planes, leading to stone surface regress. So linking back to Clactaw Broch, you can see this occurring in the Broch. In the top left-hand image, this is an image taken from Tannermore Herring Station, just to show an example of the sort of the building technique where you have the face-bedded stone surrounded by packing stone, and the face-bedded stone weathers away with the surface regress, and the packing stone then sits proud of this material. And you can see this within Clactaw Broch with surface cracking and granular losses and this surface regress of the stone. So from the observations made and the timescales associated with the weathering experiments, a decay model for the sandstone type was generated. So the stone, as we saw from the first experiment, is really robust. It will remain intact in the coming decades, but once we get towards 30 plus years of exposure to climate change, the likelihood of these clay band failures, micro cracks, and surface failures occurring becomes more prevalent. And it's important to note as well that the focus of my research is to pick out these early warning indications of how the stone might proceed to weather in a climate change future, and to try and model that within a simulated experiment. But in the real environment, in reality, these effects are going to be far more pronounced because we get occurrences of the likes of storm events, wind-driven rain, which can't be simulated experimentally. But what this research design does is it integrates climate data with building stone futures. So to summarize, heritage sites are being exposed to more extreme climatic conditions. There's no doubt about that. We have the data to support it. And this will have a destructive but relatively unknown impact on the built environment in Scotland, which is why research projects such as this are really important to try and actually understand how sites will respond. So this research using Clactol as an example serves as an attempt in the a first attempt within the literature to try and integrate the complex weathering processes with climate change data that retains relatability to the built environment and, of course, the climate data, as I mentioned. After the first experiment, there was negligible change, but with exposure to prolonged climate change condition, identified weaknesses begin to show signs of deformation. In particular, surface regress is identified as a primary way in which Torridonian sandstone weathers. We get layers of material loss. I acknowledge that's a really quick run through of quite a substantial piece of work. There was lots of analytical techniques used, which I didn't have time to talk about today. But if anyone is interested, do get in touch with me. I've got my email and Twitter account on the final slide there for you. Yeah, and thank you for inviting me to give a talk.